Today we are going to be looking at core topic in machine learning, ensemble methods. Before now, we've delved deeper into machine learning concepts such as understanding what machine learning is, and we have been able to establish that machine learning is like simply saying machine is learning. Similar to how a newborn baby goes to school, starting from basic school and learns through using data, majorly like textbooks and the rest. And then we've been able to build few models. We've also been able to differentiate between classification and regression. So by now we already know what all these things are. And our next topic today is going to be focusing on ensemble methods, which I called making smarter models by collaboration. It's actually the collaborative part of machine learning. And just like our culture, feel free to ask your questions. You can raise your hands. You can of course drop a message in the chat. You can just unmute if I'm not focusing attention there. Of course, so that I will always check either of those three channels to make sure that I'm able to pick any question you might have or clarification required. Also, remember this is going to be a collaborative section, so feel free to express yourself. I'm going to be asking you questions, and I would appreciate that you give response appropriately. Now, let's get back to ensembles. Ensembles is the collaboration of machine learning, like I said earlier, and just like natural collaboration in offices, in companies, in our work modes. When you call 3, 4, 5 people, you set up a panel of experts to review a topic. As opposed to maybe one person sitting in his office to review that same topic. That is like how you can picture ensembling. But I'm going to go deeper into this, and we explore this further. But today's objective, we'll be able to understand what an ensemble is and why it works. We'll be able to build a single decision tree. And then, of course, we spin up random forest and AdaBoost. And we also learn how to compare their performance. So you can choose the right model for your data. Now, let's get into this. Look at this picture on my screen. Please, I would like everyone to contribute at this point. Feel free to unmute at this point, or you can just drop a chat in the chat box. Look at these two scenarios: single doctor versus small board of specialists. So yeah, imagine you just run a scan, or let's say a friend or someone just run a scan, and then of course these are doctors trying to review. Let's say this is a cancer scan or whatever, and they are trying to review this. Now, which would you trust more? If you have this guy doing it alone, let's assume it's also an expert, and maybe 3 or 4 of these guys right here trying to examine this particular scan report, and these are specialists in different areas that has to do with this particular cancer or whatever is being treated. Which would you trust more? Please, I would love you to drop your comment in the chat box or on mute. Okay, James, tumor board. Okay, great. Okay, so great. So it's actually great that everyone is preferring tumor board of specialists, and of course that's how it works in machine learning ensembles too. So the tumor board of specialists is the ensemble of machine learning, and of course let's take this deeper to even then define ensembling as a base method in its own. Ensemble or ensemble learning is simply the practice of combining multiple individual models called base learners to produce a single, stronger predictor. Now, this is exactly similar to the scenario we have here. So instead of having a single model, make a decision around your result, around your output, you have like a tumor board, either making decision in parallel or making decision in sequential mode. Like one focuses on the mistake of the previous one, but we also dig deeper into this as we proceed. Now, I hope you are following me, right? Please let me know if you are following this. So we've been able to establish now that ensembling has to do with having a tumor board of specialists, tumor board of models, trying to make a decision on your data, on your output, as opposed to having a single model making that decision. Now, let's look at what this looks like. Let's say we have something like this, a random forest analogy, and then let's say we have decision tree, one decision tree, this another decision tree, this another decision tree. And then by the time you pass through this so your data set is coming to the first one. Of course, it does its things, goes into the second tree, it does its things, goes into the third tree, it does its things, and then it creates results. So you have result 1, result 2, result 3, and then the majority voting or averaging happens. Of course, as we've established previously, if you are trying to do predict discrete values, which is classification models, then we are, of course, doing a count, majority voting, and of course, if it's regression, predicting continuous value, then we do averaging. Then after that, we get a final result. Now, what has happened at this point is that this final result is able to leverage the power of these three guys to be able to make its final decision. Now, let's take this forward. Why do we want to do a tumor board of doctor? Why go from one doctor to a whole tumor board? And that would be the same question as why Ensemble. So Ensemble actually helps us do three things majorly: reducing variance, reducing bias, and combining perspectives. Now, this is just like a theoretical background of this. We still do some coding, but just like I always put it, machine learning sometimes is 50% theory, 50% coding. So you don't just want to go into coding. You want to be able to understand what is happening in every line, what is happening at every point, why are you combining these and the rest. And that is the best way you can actually be able to combine your parameters to be able to have the best performance in your model. Now, let's look at this. Reducing variance, bagging. So e.g. random forest is an example of bagging. So what are the advantages? If one doctor misreads, now, for example, let's say one doctor comes and maybe he wasn't checking something properly and he mistakenly misreads something, it can actually cause a big problem, right? So to avoid that, if 5 doctors are voting, it's easy to cancel out one individual mistake. So if one doctor misreads, the 4 other doctors are there to actually correct that misreading. Now that's that reduces variance. And bagging in its own perspective means we have those models doing their things in parallel. So tree 1 is doing its thing, going through, seeing a different version of the data. Tree 2 is seeing a different version, making its decision. Tree 3 is making its decision. And when they are done, they bring it together to, they vote to get the final result. Now, the second part is reducing bias. Now, one doctor who always default to it's probably the flu with misread conditions. But because before you even check the symptoms, you already make a conclusion to say, hey, this is the flu. And the reality is, that's not always the case in every situation. And then with boosting, each model focuses on the previous error. So boosting is like, instead of having it in parallels, they're actually making that decision sequentially. So one model finished training, tree 1 does its thing, tree 2 focuses on the errors of tree 1 and improve on that. Tree 3 does its thing and the rest down the line. And of course, this help correct bias. And of course, combining perspectives, like stacking, just combine those perspectives, like you just bring so let's say you bring Dr. Tree, Dr. XVM, and then both of them does their thing. And when they are done, they both hand over to Dr. Meta. Another algorithm would then make a decision around what is the final decision. So you can see it as a chief consultant that will be able to learn from the past cases to then make a final decision on what the judgment would be. So Ensemble itself carries this power. And if you look at some of the application of these, if you check platforms like Netflix, like even cargo competitions, most winners on cargo competitions don't just rely on a single model. Most time they stack models to be able to get their best result. So sometimes stacking is just like one of the best way to also ensure you get the best performance. We are going to code this out, and I believe we get this right. I'm going to pause a little to get questions on some of these areas that are not clear so far that you want me to go over again. Okay, you can drop it in the chat. Okay, so if I'm asking you what an ensemble is now and why it works, you can already tell me. That would be my assumption. Can someone just, probably in your own words, just tell us what an ensemble is? What you understand by ensemble? Okay. Okay. Okay, thanks, John. So that's interesting then. Yeah. So ensemble is just like you've said. It's like bringing a panel of experts to make a decision on the topic instead of using a single model. So instead of relying on a single doctor to make a decision, you bring out like 3, 4, 5 panel of doctors to review the scan result of a cancer patient and make a decision. And those doctors can either be acting in parallel, that is, they each does its things and then they combine the result, or they can be acting sequentially, like in the case of boosting. Now that's our objective 1 achieve them. Now let's go into building a decision tree. Now let's see how it works, and then spinning up random forest and AdaBoost, and then we round it up with comparing their performance. So we're going to be using cancer data. Of course, we're already talking about doctor scenario, so let's just use the breast cancer data. And the baseline tree, we're going to be using single decision tree, which we can import from sklearn. So all the models we are using, you can actually import them from sklearn. So I believe before now we already have sklearn installed on our laptops. So we just leverage sklearn to be able to do whatever we need to do. And at the end, we print the cross validation score accuracy for each. Now let's delve into this. From sklearn.tree import decision tree classifier. Now before then, let's import from sklearn dataset import load. Please, if you are not getting anything, whether it's coding, whatever I'm doing, please feel free to stop me. The entire idea of this is that not how far but how well. We need to actually, I need to be sure that you're actually picking the best value out of this. Now I'm trying to, so let's we need to actually comment this properly, but maybe let's just do the little we can do because of our time today. So we're going to just use this for import. So let's make this import required libraries, or let's just say import. So this is where we're importing required libraries, data set, and the rest. So the first thing we need to import is import our data set. So I'm going to add a comment to this as we are done, so that by the time I share this with you, you're also able to follow through. But please follow through what I'm doing. That's why I want to type this in real life instead of just showing you a ready-made one. So load breast cancer. So this is a data set we're going to be working with. Now we need decision tree classifier. That's a single tree. Remember the single doctor. We also need from sklearn.ensemble. We need to import a random forest classifier, AdaBoost classifier, and yes, from sklearn.model selection, let's import model. Let's import cross val score. Now, all things being equal, if you have your library installed, sklearn, you should not get an error. So that's running fine. Now let's go ahead to actually now run this in real life. So I'm trying to check our timing to be sure we are still, yeah. Now let's load the data set to start with. So we've imported. Now load data set. And let's also make this heading 1. Mark them. And let's do something like x comma y. We already know what x, we are already used to the nomenclature of x and y during our linear regression section. But let's load this, how to load this particular guy. So we are loading this guy, load breast cancer, and we are returning x, the comma y is equal to true. Now if you check your x now, it should have a value. So let's just check the first instance of x. So you can see it's like the features, and then let's check the first instance of y, and these are label. So of course, we're trying to, we can see that this is a data trying to predict a discrete value, right? Now let's go deeper into this. So let's go deeper into this. We have 5 more. Okay, yeah. So let's go deeper into this. Now, let's just build the first tree first, or let's build these in parallel. That would actually be great. So let me define the models as a dictionary, or like let's do this simultaneously, and then we're going to be doing decision tree classifier, and of course this guy. We are going to be doing random forest classifier, and that's this guy. So we just go with the default parameters. So for example, like we have, if you want to see parameters, like as usual, you can press shift tab on your laptop, and then you can see default estimator is 100 and the rest. So we just go with default number of estimators, and then we're going to try AdaBoost classifier, which is an example of boosting. So this is bagging and this is boosting. Now we're going to be using these 3 guys. Now to use them, we can just write a simple loop for name, comma model in models.items. And now we can actually calculate the score from here. We can do cross-var score. And then we can supply the model, the X, the Y, and we can set the number of fields classified. Now we remember our cross validation from our previous topics. It's majorly like breaking our data set into like 5 different parts, and then we use each of the parts for testing. So it's like saying you want some a candy. You decide to say, oh, there are 5 bags of candy, so I can finish eating candy in the first bag, write my taste, my satisfaction, eat the one in the second bag. So it's like I'll do the same thing for the entire 5 bags. So at the end, I'm able to test the 5 bags without either of the bags being too lucky. So these are like what we are trying to do here. But of course, we've used this in our previous sections. So let's just print what the result looks like. Now, let's print name. Sorry. So name food accuracy is X is score. Let's also print the mean. So we need the score, the mean, and the standard deviation. So we have the mean accuracy is score dot mean to 2. Then we have the standard deviation. Let's do this std. Just std is score dot std with a 3f. Now our model is ready. Now let's check this. Let's interpret this quickly. Let's compare before we run this up. Now comparing this is actually very straightforward. And then you will be concerned on why is Femi doing standard deviation and why is Femi doing mean. And what I've done here is straightforward. I imported the libraries, load the data set, and then I define the models here, and then look through the model at the same time. So instead of doing this one after the other, this is like a quick way to make this shorter, and then of course we can also see the results straight away. Now let's compare this. I can say in a normal typical comparison, you can easily look at the accuracy, the mean accuracy. This is 91, this is 96, this is 97, and straight away someone can say, hey, guy, AdaBoost wins. But not in all cases. Now, let's look at it this way. Another way to look at ensemble. Ensembling is not about sometimes having a model that is sometimes always like around 97. No, that's not what you want. You want a model that will always be around 97, not a model that is once in a while 97. So there are 2 different ones. So if it's always 97, you are confident if you are predicting with it, your confidence value is around 97. But if it's sometimes 60, sometimes 90, sometimes 80, sometimes 100, what you are simply saying is your next prediction, you are not sure if that prediction is 20% or 60% or 90. And that would affect your confidence level. So sometimes accuracy is what we check, but let's look beyond that. So by accuracy, we can say AdaBoost wins. But not just that, we need to check other things. Now, we need to check the standard deviation. The standard deviation for this guy is 0.40. Now, the lower the standard deviation, the better. That means, of course, it's closer. If you look at the data, of course, we know standard deviation is trying to measure the distance between this data from the mean. We've already talked about those statistical background foundation at the beginning of the section. Now, if you look at this, we could see this guy sometimes is 90, 91, 90, 93, 90. So it's always around 90. So that's why the STD is around 14, still very low. Now, this guy is 96, but higher standard deviation. If you look at it, sometimes is 93, sometimes is 97, sometimes is 98. It's actually everywhere. Now, look at this guy. Sometimes it's 95. Sometimes it's actually between just 95 and 99. Like, that's what explains why the standard deviation is low. So if you are looking at this model, we would say AdaBoost wins because it has the lowest standard deviation and the highest accuracy. Thanks for joining this section, and then we take questions and answers now. If you have any question, please drop on the chat. We respond to this. In the next section, we're going to be focusing on stacking. How the stacking works. Stacking models and the rest. But yeah, thanks for joining today's section, and Bye for now.